Here's a physics puzzle that has challenged engineers since the 1940s. How do you deliver a payload 1,000 kilometers away, traveling at 5 times the speed of sound, and hit a target the size of a building? The speed part is relatively easy. Rockets are simple machines. The hard part is accuracy. At Mach 5, a 1-degree error means missing by kilometers. Between 1980 and 2026, Iranian engineers tackled this problem. Not by building perfect missiles, but by making strategic trade-offs between speed, precision, and survivability. This is the engineering story of how physics constraints shaped a missile program and why some problems remain unsolved.
Welcome to SciCuriousID, where curiosity meets science.
Every rocket, from fireworks to intercontinental ballistic missiles, obeys the Tsiolkovsky rocket equation. Delta V equals V times the natural log of m0 over mf. In plain terms, the speed you can achieve depends on how fast your exhaust moves, and how much of your total mass is fuel versus structure and payload. The engineering implication: to fly 1,000 kilometers, you need a delta V of roughly 2 to 3 kilometers per second, accounting for atmospheric drag and gravity losses. This requires high-energy fuels, minimal structural weight, and efficient staging. But here's the constraint: Iran couldn't acquire the best fuels or the lightest composites due to sanctions. They had to solve the rocket equation with suboptimal materials. This is like building a race car with a standard engine and steel frame instead of carbon fiber. You can still win, but you need design ingenuity to compensate for material limitations. The result: Iranian missiles tend to be heavier and less efficient than Western or Russian equivalents, requiring larger fuel loads and bigger engines for the same range. Rocket propulsion presents a fundamental engineering trade-off: liquid fuel versus solid fuel. Liquid fuel systems, like the Shahab 3, offer higher specific impulse, more energy per kilogram, and can be throttled or restarted. But they come with disadvantages: complex plumbing, cryogenic storage issues, and lengthy pre-launch preparation. Crucially, they are visible to satellites during the fueling process. Solid fuel systems, like the Sejal, are simple, reliable, and capable of an instant launch after being stored for years. The trade-off is a lower specific impulse and the inability to throttle or shut down once lit. Iran's early missiles used liquid fuel because the technology transferred from North Korea and Russia was liquid-based. But this created operational vulnerability. A liquid fuel site is detectable during the 30 to 60-minute fueling window. The evolution toward solid fuel, starting with the Fatih's 110 in the early 2000s, was driven by survivability requirements. Solid fuel increases the probability of surviving to launch. When you can't hide the missile, you eliminate the detection window. This is classic constraint-driven engineering. Part 3 will cover the guidance challenge. Here's where physics gets genuinely difficult. A ballistic missile follows an elliptical trajectory up out of the atmosphere, coasting in vacuum, then re-entering at hypersonic speeds. The problem is that small errors early become large errors late. Sources of error include the launch phase, mid-course, and re-entry. The accuracy problem: early Scud missiles had a circular error probable of 1,000 meters, essentially area bombardment, not precision strike. Improving accuracy requires better inertial guidance, precision gyroscopes, and accelerometers. It also requires terminal guidance and countermeasures against jamming. GPS denial is a real threat. The engineering reality: Iran has struggled with precision guidance technology due to sanctions. They've had to reverse engineer components or accept lower accuracy in exchange for availability. This is why Iranian missiles evolved toward larger warheads, engineering compensation for guidance limitations. Part 4 will examine the short-range solutions. The Fatih 110 represents Iran's first successful solid-fuel tactical missile. Let's examine the engineering. Design specifications: a range of roughly 300 kilometers, a large 500 kilogram warhead, and inertial navigation with GPS assist. Launch time is measured in minutes rather than hours, and the system is fully road mobile on a truck-mounted launcher. Engineering significance: this is a system solution, not a technology breakthrough. The Faith 110 optimizes for survivability, responsiveness, and manufacturability. The trade-offs: shorter range, lower payload efficiency, and simpler guidance for better reliability. The Zulfaha evolution, extending range to roughly 700 kilometers while maintaining solid fuel simplicity, required improved propellants and lighter casings. It also featured a possible maneuvering re-entry vehicle, or MAR-V, for terminal correction during the final approach. If true, this represents the ability to adjust trajectory in the final seconds, dramatically improving accuracy despite guidance limitations. The engineering direction is clear: compensate for guidance limitations with terminal maneuverability. Part 5 will examine the liquid fuel compromise. The Shahabs 3 and its derivatives represent the strategic reach layer, but also illustrate engineering constraints. Technical specifications: a range of roughly 1,300 kilometers, a massive warhead up to 1,000 kilograms, and propulsion based on liquid fuel technology. Liquid fuel provides the energy density for long range, but it creates fundamental operational fragility. The missile must be stored unfueled and requires a 30 to 60-minute fueling process before launch, supported by a massive convoy of trucks. This makes it vulnerable. US and Israeli intelligence can detect fueling activity through thermal signatures, vapor releases, and equipment movements. The Shahab 3 is therefore a second strike weapon, useful if you survive an initial attack, but highly vulnerable to preemption. The Ahmad upgrade represents guidance engineering overcoming propulsion limitations, adding 4 control fins for terminal guidance. Claimed improvements include reducing the circular error probable to roughly 50 meters, a significant leap in precision if accurate. But the fundamental vulnerability, liquid fuel preparation, remains. Part 6 will examine the solid fuel breakthrough. The Sejal missile represents Iran's attempt to solve the survivability problem without sacrificing range. Engineering specifications: a range of up to 2,500 kilometers, 2-stage solid fuel propulsion, and the capability for an immediate launch from a mobile platform. The 2-stage design: Stage 1 boosts the missile to altitude, then Stage 2 reignites or burns continuously for range extension. This is staging optimization, dropping the heavy first stage casing to improve the mass fraction for the second stage. The Sejal eliminates the liquid fuel vulnerability window. It's always fueled, always ready, prioritizing survivability over raw efficiency. The Challange variant takes a different approach, a large liquid fuel missile capable of carrying a massive 2,000 kilogram warhead. Engineering trade-off: maximum payload versus maximum survivability. The Challange accepts vulnerability to deliver massive warhead capacity. Recent analysis suggests Iran may need to reduce payload mass to achieve reliable range with this design, a classic mass fraction problem. But engineering targets are moving higher. Part 7 will examine the controversial hypersonic claims. In 2023, Iran unveiled the Fateh, or Conqueror missile, claimed to be hypersonic, capable of Mach 5+ with maneuverability. The physics reality check. Hypersonic flight creates extreme engineering challenges, starting with heat. Air friction creates plasma at temperatures exceeding 2,000 degrees Celsius. Control surfaces fail in plasma, requiring thrust vectoring, and the plasma itself blocks radio signals, meaning internal guidance must be fully autonomous. Materials must withstand intense thermal shock while maintaining their aerodynamic shape under extreme pressure. Iran's claims are bold. A range of 1,400 kilometers, speeds up to Mach 15, and maneuverability during both powered and unpowered flight. But skepticism remains. The March 2026 tests resulted in failures, one malfunctioning in flight and one intercepted, with analysts noting poor accuracy at distance. This is common. Announce aspirational capabilities to deter adversaries, then work backward to achieve them technically. Engineering is slower than propaganda. Even if only partially successful, the fatter represents the correct evolutionary path. Speed plus maneuverability plus accuracy equals a system that is harder to intercept. But the physics are unforgiving. Part 8 will examine the defense counter-engineering. Every offensive system creates selection pressure for defense. The story continues with the systems designed to stop them. The multi-layered defense architecture consists of 5 specialized systems, starting with Layer 1, Arrow 3 for exo-atmospheric interception. Arrow 3 uses kinetic kill vehicles mid-course, while Arrow 2 handles shorter-range ballistic missiles within the atmosphere. Layer 3, David Sling, targets cruise missiles and slower threats, while FAD provides terminal high-altitude area defense in the final phase. Layer 5 is the adapted Iron Dome, designed for short-range rockets at a cost of roughly $50,000 per interceptor. The economics: Iranian ballistic missiles cost roughly $1 to $2 million each. Defense interceptors, like the Patriot, cost $3 to $5 million each. This creates mutually unsustainable economics. Iran can't afford endless missiles, defenders can't afford endless interceptors. Defenses have evolved toward directed energy, like the ion beam laser system, electronic warfare, and networked radar for earlier detection. No defense is perfect. The engineering goal is probability reduction, not absolute protection. Part 9 will conclude with the systems lesson. What does this engineering history teach us? Lesson 1. Physics constraints are non-negotiable. You can't negotiate with the rocket equation. Iran's program advanced within hard physical limits: energy density, mass fraction, thermal tolerance, made difficult by sanctions. Lesson 2. Operational requirements drive design. The shift from liquid to solid fuel wasn't about performance, it was about survivability. Good engineering solves the right problem, which isn't always the technical optimum. Lesson 3. Accuracy is harder than range. Extending range requires more fuel, improving accuracy requires precision manufacturing and quality control. Iran has demonstrated range, but the March 2026 failure suggests guidance remains the unsolved problem. Lesson 4. Claims exceed capabilities. The fatter hypersonic missile illustrates a common pattern: announce capabilities for strategic effect, then struggle to achieve them technically. Engineering is slower than propaganda. Lesson 5. Defense adapts. The threat drove investment in layered defense. This is the Red Queen dynamic. Offensive innovation triggers defensive innovation, which triggers new offensive approaches. Stasis is temporary. Lesson 6. Cost determines strategy. At $1 to $2 million per missile versus $3 to $5 million per interceptor, the exchange is unsustainable. This creates strategic stability through economic exhaustion, a Cold War logic applied to regional conflict. The next time you hear about ballistic missiles or hypersonic weapons, remember, this isn't just about military power. It's about engineering within constraints, the same challenge faced by any designer working with limited resources and hard deadlines. Iran's missile program shows that physics limits are real. You can't hype your way past the rocket equation. Trade-offs are inevitable: speed, accuracy, survivability. Pick 2. Systems adapt. Today's advantage is tomorrow's vulnerability. Cost matters. The cheapest solution that works beats the perfect solution you can't afford. These principles apply to clean energy, transportation, medical devices, any field where engineers solve problems under constraints. The missile is just a projectile. The engineering is universal.
Thanks for watching SciCuriousID. Until next time.